Good morning. Today I would like to talk to you about paralleling power generators and the physics involved and the theory. Kind of sounds a little bit boring, but it may help you to prevent damage to your generator sets. And I actually have to print some stuff out here to get this somewhat scripted because that is fairly theoretical, this whole thing. I used to teach classes for IEEE, and I haven't done it in a while, so you just want to stick with me on this one here. I'm doing this today because I looked at these boards and I watched some other videos on YouTube what other people did and how they paralleled their units, and from a professional point of view, you can really get into trouble with this thing when you do it the way people suggest of doing parallel operations, especially on the MEP 002A, 003A, on the 5 and 10 kilowatt units, since they don't have a syncing connection or control circuit involved with it. That becomes really tricky, and I will explain this. I think the easiest way of explaining on how this actually works is we're just going to start with a DC circuit. Let's just assume you've got two batteries, and we're going to parallel two batteries, two car batteries, regular 12-volt car batteries. And the schematic for this would look like this. You have the plus, minus. This is battery 1. And then we're going to go over here. This is our battery 2. And we connect those. And we put a resistive load on here. And let's just say this is battery 1, that one. This is battery 2. And what we're going to do here is we're going to draw a load current, IL, of 1 amp. And both batteries have exactly 12 volts. That means they're exactly fully charged to the same level and they're having exactly the same voltage. Now what will happen is the load current of 1 amp is going to be split up. You're going to have 0.5 amps from this and 0.5 amps from this battery. Both of these batteries, of course, they have an internal resistance, very, very low resistance built in, where we have a dropper boost. What I have basically drafted here is an ideal battery, which doesn't exist in the real world. But you can see the load is exactly split between the two, and this comes from an ideal situation. Now, you probably know from experience that most of the batteries you find will not have a exact voltage. They're never going to be exactly identical when you put them together. Now what will happen in let me wipe this out here. In a normal world, what's going to be happening here is that the currents are going to change. Let me change the load here on this here. Say we have now a load of 10 amps. And we have a load resistance. Oops. Now we're going to go with a 100 volt battery. That's what I calculated here, what we got. Let me just change this here over and I'm going to explain this. So the first battery has 100 volts and the second battery has 102 volts. Just to make the math simpler in this, the resistance is 100 ohms resistive load, not inductive. 100 ohm. Then now the internal resistance is 0.1 ohm here and 0.1 ohm on this battery. They're both identical. We're having exactly the same type of battery, but both batteries have a different state of charge. Now what will happen is our 10 amps will divide as follows. Now actually we're having a 1 amp, we're having a 1 amp resistance. 100 ohm by 100 volts gives me 1 amp load. And now what happens is the current in this battery here is going to go in this direction. It's going to be 9.5 amps. Now you're going to ask why. because the entire load is going to be 10.5 amps here. Now this is going to break out as follows. It goes up from this battery here, then it's going to split. The 9.5 amps are going to go from this battery over to this here. And 1 amp is going to go over to your load. And this is basically, this battery here, the battery 2, since it has a higher charge and a higher voltage, is going to try to charge this battery here, bringing it up to the same level of voltage. They're going to seek an equilibrium. And so besides of having a load current going through the battery, now this battery has to also provide an additional 9.5 amps, which calculates itself out of the internal resistance of the battery. And this way you can actually determine this. So now this battery here will basically, over a period of time, this voltage is going to come down, this voltage is going to come up, until they both have reached an equilibrium. Once they have both reached an equilibrium, the current here will drop off, this current will drop off, and then you will have only the load. So in the beginning of the system, when this is first hooked up and connected, that's basically what you're going to have. And that is important when you work with power supplies or with systems like solar panels and battery chargers for windmills, because you usually parallel a bank of regular lead-acid batteries, and then you're actually going to have and you series them, so you have series and parallel connections. And when they're first hooked up, before you charge them, you have to let this whole system sit for several hours until there is no more currents going between any of the parallel batteries. And then once the system has stabilized, you can actually apply a charge, and it will distribute itself through the system, what you got here. Now, why am I showing you a DC system if we're talking about an AC generator? This is what happens in generators. That is the same for AC and DC generators. If you have two different voltages coming out on these systems, which are not exactly 100% equal, especially with a manual knob and a gauge, you know, you have that analog voltmeter there built in these generators, they will never tell you exactly the voltage. So one of the first conditions before anything happens, before you can parallel anything, is you have to make absolutely certain that both of your output voltages are exactly the same. And this is why these O2 and O3 generators are not quite suitable because of the tolerances involved, which means whatever generator has a slightly higher voltage is going to push a current into the lesser voltage generator. And that can be excessive, especially on these 10 kWs. You can draw several tens of 20s or 30s or 50s of amps, depends on what configuration you have. That will overheat your generator on the lower side, because your generator is not really a battery, but it is actually a generator with a coil. So you're actually feeding a rather large current at that voltage which you have selected into the other generator set. So, you know, people were hooking this up with these light bulbs to sync them because they're out of phase. The out of phase thing is a different issue altogether. It's by far more complex than this. This is the first basic. So what actually would have to happen is you would have to use a high precision digital meter to exactly set the RPMs equal to each one of these generators, and you will have to set the voltage correct. That means both of these outputs have to be exactly at the same voltage. Otherwise, you're going to have currents going in either direction between the two generators, which are not going out to your load. That is probably the first big part in this whole system, by trying to parallel generators which are not really meant to be for parallel operations. Now, if, for instance, if we had a circuit where both of the rheostats, which they call them, which are basically potentiometers, bigger size potentiometers, would be controlled, so each generator controls the other rheostat automatically according to the voltage, then you can actually level this out. The voltage on the O2 and O3 series are basically controlled by the rheostat, which feeds into the circuit board, the voltage circuit board, which is on the left-hand side inside the cubicle. And that brings out the excitation voltage out to your generator set, to the excitation coils. And depending on what voltage you're setting this, that's how you can basically regulate the voltage output of the unit by regulating this. So each unit would have to control each other, the other unit's voltage output until they actually come into sync. We could build the circuit board for this. That is definitely possible. It requires some major rewiring of this entire set, and you would lose basically the rheostats which you have on there. So that means once this thing is basically wired for parallel operation, you will not be able to really run this on a single or one generator by itself. That's kind of where that is it. Now let's talk about the other issue in this. Now this was with a resistive load, and I don't know how advanced you are with electronics. I'm going to skip through this. The next problem we're actually having is with this setup that I saw on YouTube, was that the fellow basically used this generator. I'm going to have generator 1 here, and this is set to 120 volts AC 1 phase, to make it simple. And then you have here generator 2, 120 volts AC 1 phase. So now what the guy basically did is you're going to have L1 is here, and you have LO, which is this terminal here, and then you have L1 on this generator, and this is LO. Now he used the two 5 kilowatt units, the OO2s, OO2A, and what he did is basically he put a light bulb between these two phases, and he connected those straight together. Now what will happen is, and now a light bulb is a resistive load, and a resistive load behaves without any problems. This is the easiest circuit to actually hook up. The only things you really have resistive loads in your house is basically a regular light bulb. There's not much resistive. And a heat element, if you've got a regular heater without any fans in it. That is usually all resistive. Everything else in a regular house, if you want to utilize this to parallel to units, to do an automatic transfer switch backup system for your houses, you're going to run into a problem is that most of your loads in your house are all inductive loads. And I will get to this here. This will be the next step. So we're talking now about a resistive load here when they do this. Resistive load. When the units are basically off, you have a sine wave coming out here. It looks like this over T. This is the time T going in this direction, and this is your voltage going up in value. You see this